Okay, let's go ahead and get started on our final week with all three of you that are here. People will walk in a little bit late. I think we've got some people that are in. Hi, Lauren. Thank you for coming all 4 weeks. I think that people will probably walk in like they did last week after their, I don't know if it's rounds or clinics or something that's going on. So our final week, we're going to get back into inferences. We're going to look at some specific hypothesis tests that are very common. Last week, if you'll remember, we covered the experimental situations where we were interested in looking at how means are different between groups. So we covered the t-test and analysis of variance. This week, we're going to talk about the same kinds of experimental situations where we have maybe a single group or multiple groups, and we're interested in how a proportion or some kind of categorical outcome differs between groups. I guess you guys would need to see the screen. There, sorry about that. So again, we'll cover the most commonly applied test, which is the chi-square test. We'll also look at regression methods. This does not look like my most recent PowerPoint, so give me just a moment to make sure that I've got the right one. Oops. I think I grabbed the wrong one. Yeah, I did. I always make last-minute changes, so let's restart this. Close out the old one. So again, we'll focus on a similar experimental situation where we have categorical outcomes rather than continuous outcomes, looking at response rates essentially between groups. We'll look at survival analysis methods, which are specific for cases when you're interested not only does an event occur, but what's the timing of the occurrence. And then also we'll look at different ways of adjusting these common experimental situations, these comparisons for other additional factors that we typically call prognostic factors. And those methods are regression methods. The first example that we have here is again looking at a categorical outcome. And we don't really have multiple groups. We have a single population. Perhaps a genetics example would be a great way to look at this. If you have a sample or a small sample of patients and you're interested in how do their genes, what do their genes look like, you may hypothesize that there's a particular fraction of individuals who have a certain type of genetic marker, for instance. So here, a very simplistic example, we take a sample from this population. We think in the population about 75% should have this trait, which we'll call capital A, and we think an additional, the remaining 25% have some different trait, capital A, small a. So here our dependent variable could be the count, but it's really the number of samples out of 100 that we're going to take from this population that demonstrate each of those particular features. You hypothesize that the population of interest has that 3-to-1 ratio. So you think 75% have one trait, 25% have another trait. You actually think that it's higher than 75%, but that's the smallest, sort of that lower bound on your proportion of interest. Your null hypothesis looks something like a statement about a proportion. Sometimes in textbooks or in notation you'll see proportions represented by this pi, which is just a Greek letter that corresponds to our p. Other times you'll see it actually represented by the p. But here we're looking at whether or not this proportion of interest is 75% or 0.75 or is it not. So it's the usual null and alternative setup where we have the null representing an equality statement and alternative representing some difference from that value. This type of test is referred to as the chi-square goodness of fit test, because you're basically saying this is what I think the distribution of levels is in my population. Is my guess correct or is it off? The chi-square goodness of fit test will basically take what you have hypothesized in terms of the fractional breakdown of these features in the population and compare it to what you observe in the data. So just like the t is a measure in terms of standard deviations between what was observed and expected, the chi-square is doing the same thing. We won't get into the mathematics of it because it's not quite as easy to see as the t statistic is, but just know that what you get with the chi-square is very similar to what you get with the t. So the bigger the statistic, the more discrepancy there is between the hypothesized breakdown and the actual observed breakdown. Suppose you take 100 samples, 100 people, or 100 different samples, and you count the number in that sample that have each of these features, and it turns out you hypothesized it was a 3-to-1 or 75-to-25. What you actually observe is 84 and 16, or an 84 to 16% breakdown. So is this different enough from what we hypothesized to conclude that the population rate or proportion of this characteristic, which we call capital A, is really 75%, or does it appear that it's different than that? Just like with the t-test and with ANOVA, we do have some assumptions that we have to verify first. For the chi-square test, it really only revolves around the sample size. So you have to make sure you have enough data, a big enough sample, that none of your expected frequencies are less than 5. The way that you do that, if you'll remember, pi was your hypothesized proportions for your categories. Take those proportions. In our case, it was 75% and 25% from our hypotheses, and multiply them by the sample size of your study. So if 75%, well, obviously 75% is the bigger one. The easiest way to do it is start with the smallest, and if the smallest meets the criteria, then you don't have to worry about the rest. So take 25% of your sample size and make sure it's bigger than 5. In our case, we have 100 samples. So 0.25 times 100 is 25. So we meet the criteria for performing the chi-square test on this data. If we didn't meet that criteria, there are options that we can do that don't have these sample size restrictions. They're called exact tests. In this case, the binomial test would be the appropriate test for this kind of data because we have binomial data. So we have this breakdown. The way that we would perform this test in RStudio is through the function chi-square, CHISQ.test. If you have a data set, I'll show you the structure of that data set. You tell it which variable contains the count and call that x, and then you give your hypothesis as what we call a vector. So again, this C means basically combine these two elements into a single object called P. This is the hypothesized proportion for the first category and the hypothesized proportion for the second category. So we think it's a 75-25 breakdown. We're going to compare that to the actual observed counts that we got in our data set. I gave you here the actual hand calculation for the chi-square statistics, so you can see that it is truly some measure of the difference between observed and expected. If we go into RStudio, actually, I didn't pull over the test data sets. Let me see if I did. I know I didn't. Okay, so I won't be able to do this example in RStudio, but my test data set I can describe for you has a single variable, column variable, that represents the level of that category. So I have a column that looks like capital A. I can probably make this for you just as fast as I can describe it if I have Excel on this machine. There it is. So we often have our data sets in Excel. So let's say we have our feature, we'll call it feature, and then we have the count. So we had capital A, lowercase a, capital A, and then we had 84 and 16. R, unless you do some additional work, will require you to, where's the desktop? There we go. Will require you to save this as a comma-separated file because it likes the comma delimiters, or like a tab delimited file. But this is the easiest way when you have Excel data. CSV, just save it. Yes, I want to keep it in that format. I'm going to close it out. And now the way that you would import this data set into RStudio is right over here in the upper right-hand corner. Import it. You can import it from the internet if it's a web-based data set, but more than likely you have it somewhere on your machine or on a network folder. And I can go to that place and open it, and it will give me a preview of what the input file looks like. Notice it looks like a comma separated, which just means if I have something and then a comma and then something else, R will read this as two different things. It will read the first row if you have your variable names as the variable names, and it will read the subsequent rows as actual records in the data set. You can change some options here, but again, if you've set it up this way, you can see down here how it will import the data set, and then it will show you the data set here once you get it in. So now that I've actually got that, I can attach that data set, test 1, to my console so I can work with it. The chi-square test, we have to again give it the variable name for the count. So in my data set, I called it count. So I'm going to say use that count variable. That gives you the frequency distribution of this genetic trait, and I'm hypothesizing that it should be 75 and 25. Is it different enough for us to reject the hypothesis? So if you just run that, either copy it and paste it down in the console, or some other way, there's point and click methods of running, like here. We see the output of the chi-square test. The chi-square test will tell us what our data set is. Here's the chi-square test statistic, 4.32. The degrees of freedom for that test statistic is 1, but the p-value is 0.03767, which, if we follow the general convention of comparing this to 0.05, in this case we would reject the null hypothesis. So if we go back to, looks like we have, okay. If we go back to our slides, the interpretation of that p-value is that the hypothesis about the population ratio being 75-25 or 3-to-1 is incorrect. It does not appear that that hypothesis is correct, simply because what we observed was too different from what we would expect under the null hypothesis, and that p-value is 0.038. Another example, I guess I should pause and see if there are any questions about this. One of the biggest problems, I think, when doing an analysis is the structure of your data. So sometimes your data will look like that test 1 data set where you have just the level and then the count. Other times it will be in what's called case form. So I do have an example of case form data where we actually have to restructure it. My advice to you would be to find ways, either software packages or other automated ways to transform your data from one structure to another, whatever the structure is required for the function or the analysis to be performed in. Simply because if you do manual data entry from one structure to another, you're increasing the chances of a data entry error, and you could actually cause problems with your analysis. Here's another example looking at tumor response and treatment. Both of these, notice, are categorical variables. One, treatment, is a nominal variable. It's just A or B. Our response is ordinal, so it's still categorical, but the response outcomes have some natural ordering. You can either have a complete response, which is the best kind of response to have. You could have a partial response. You could have stable disease, or you could have a treatment failure. Oh, it says hair color. That's terrible. This was an old example that I had pulled up, and I had a different example scenario and forgot to change this to response. But regardless, our response is this column variable, complete, partial, stable, failure, and then our row variable is the treatment. And this is very often how we present data when we're looking at the association between two categorical outcomes. What we're really trying to figure out here is whether or not treatment has any impact on how people respond, how their tumors respond. So since we're looking at an association between these two, what we're going to use instead of the chi-square goodness of fit is what's called a chi-square test of independence. The hypotheses revolve around whether or not response is independent of treatment, which means that the response rates are the same across all treatments, or is the response dependent upon treatment, which would, of course, indicate that response rates are different. And maybe we have a treatment that's a better performer in these kinds of tumors than the other. So just like in the previous example, the only assumptions that we have to check are related to the sample size. So we have to look at our proportions and do a simple calculation comparing our sample size times our expected proportions to 5. It's not quite as easy here because we don't explicitly state we think that in treatment A, complete responders will have there'll be a certain proportion of complete responders. But the nice thing about statistical software is, for instance, if you're using SAS, if you're using SPSS, if you're using R, it will shoot out a warning. It may give you the results of the chi-square test, but it will have a big warning at the bottom that says, stop here, the results may be invalid because you have some expected cell frequencies that are smaller than 5. If that's the case, then you could do a Fisher's exact test, and I will show you the code for both of these. So again, we're asking ourselves the question, does it appear that this type of sample could come from a population where the rates of response are occurring with the same frequency within each treatment, or does it appear that response is associated with treatment? In other words, one of these treatments is causing some shift or some change. A could be a new therapy under consideration, and B could be a standard of care. The way that you would do this is you would have a data set where the first variable, each row would correspond to one patient. Each column would correspond to what treatment they received and what their response was. So if I have 300 subjects in my clinical trial, I should have 300 rows in this data set. 300 measurements of treatment, 300 measurements of response. That's not always how we get the data, so you would have to do a restructuring. So my test 2 would look like, and again, I did not move these data sets over, but I can show you what they look like very quickly because it's easy to enter. So I'm just going to transpose I'm going to put in the sample sizes for treatment and response. So I have 4 possible combinations of treatment and response. These are basically my 8 different cells in my table, and then I have a number of subjects who got treatment A and then subsequently had a complete response. So that's these entries in my data here, in my contingency table. So 32, 43, 16, my enter key's not working, 32, 43, 16, and 9. And then for treatment B, 55, 65, 64, and 16. I'm going to call this test 2. And again, if you have it in an Excel workbook, just convert it by changing the type to a CSV and hit save. And then you can import it. Take a look to make sure that it looks correct. I end up with a column for treatment, a column for response, a column of counts. If I want to call on these individual variables, I have to call them by name. So I'm going to attach my test 2 data set to the window here so I can work with it. And I mentioned earlier that sometimes the way we have our data structured is not the way that we need it to be structured in order to do analyses. So my recommendation is never to hand transform. If you can probably go online and find software that will transform data from what's called wide to long, or in this case from what's called frequency form to case form. I'm not going to get into this function. I simply put it here because I didn't want to enter in all of that data for 300 people. But this function that I've got here, it's called counts to cases, is something that I found online. I didn't have to write it myself. I went out and Googled it because R is really nice about that. I said, you know, I've got data that has a count variable, but I want it to be one row for each person. So how can I do that? All I have to do is go out, somebody's written a function, I can grab it. There's actually another package in R called reshape that will do it even more easily than this. You tell it, reshape my data from wide to long. So if I run this, and then I run a line that says, please create a new data set from my old data set test 2 using this function. And then if I look at the test2.cases, this new data set that I created, automatically, without me having to do any data entry, in a couple of lines of code, I created my case form data set. So now instead of having the 3 variables, one for treatment, one for response, one for count, I have a data set now that has a variable called treatment, a variable called response, and 300 records in it. If I click on that, I can actually see what it looks like. And this is the structure that the data has to be in order for it to work with the chi-square.test. The way that I do the analysis is I tell it what one categorical variable is and what the other categorical variable is. So here in my data set I had treatment and response. And this is the call to the chi-square test. It tells me Pearson's chi-square test results in a chi-square statistic of 8.9872 with 3 degrees of freedom. The degrees of freedom are related to the number of rows and number of columns in that original data, that original contingency table that I showed you on the PowerPoint. And then the p-value for this test is 0.02946. So again, if I'm doing the usual comparison at the 5% level of significance, then here we would assume, or we would conclude that treatment and response are not independent. In other words, that these treatments are resulting in different rates of response when our response looks like this ordinal categorical variable. If I wanted to do the Fisher's exact test, I still have my data in the appropriate structure. It would just be the Fisher.test. And the resulting p-value that comes out. There's not a test statistic per se from the output, but the p-value is 0.0241, which is very similar to our 0.02946 from the chi-square test. The way that we would visualize this is, in general, for the association between 2 categorical outcomes, you like to see what's called a grouped bar chart. So I have here on the x-axis my independent variable, treatment A and treatment B, and then the bars are differentiated by my dependent variable, the actual response rates. So what we can see here very quickly, look at the difference between the yellow. It appears that treatment B is resulting in more stable disease, percent-wise, than treatment A. And that's at the expense, it looks like, of these complete and partial responders. We have a much higher rate of complete responders and partial responders together than in A than we do in B. And that allows us to discuss what the statistical significance and the actual, if you will, effect size is here for the difference between A and B. Any questions about the chi-square test of independence? If you're at the beginning of a study where you know, based on the design of your experiment, your research question, the type of data that you have, you may be interested in how many observations do I actually need? How much data or how many patients do I need to get data on in order to adequately power a test like this? Here's a simple example that comes from a reinfarction trial research group from 1978. This comes from the Pocock text on clinical trials, which is a very good reference text if you're interested in just looking at different aspects of clinical trials. They have here, they're trying to design a randomized double-blind trial comparing one treatment to placebo. I'm not going to try to say these words because I'm not going to be able to say them correctly. And they're giving them these treatments to patients after they have myocardial infarction. The questions that we would have to ask ourselves prior to actually powering the test are, what is our design? In other words, are we randomizing? How many groups do we have? What is our outcome? That would allow us to determine what analysis plan should be put in place, and then from the analysis plan we can then calculate a minimum sample size or an estimate of our sample size required to have adequate power for the primary objective. So here they're looking to see if the treatment is of value in preventing mortality after a heart attack. The primary outcome that they're looking at is whether or not a patient or a subject in this trial dies within the first year of treatment. So that's just coded as a death or not within 1 year. This is binary data. The data analysis plan would include something like a comparison of percentages of patients dying within the first year on the treatment, which we'll call P1. That's the proportion or percent of patients dying on treatment versus placebo, P2. The simplest analysis would be the chi-square test, and we could decide prior to doing this that we want to have a type 1 error rate of 5%, meaning the threshold of evidence required for rejection is set. I have to make my p-value be at least, at the most, 0.05 for me to conclude that we have some impact on the mortality of these patients. The way that you would power the chi-square test is actually very simple and straightforward in this case because we have a placebo control group. So we would probably know at this point what the expected results would be under placebo because we've probably had patients with this condition and we know their survival. We've got good estimates of their survival within 1 year. So since we understand how patients tend to, what their survival looks like after heart attack, we could specify what we think P2, the proportion of patients dying within 1 year after placebo, would be. And it turns out we would expect in this study for it to be about 10%. So that allows us to specify our best guess for the control group. That's not always this easy because you may be comparing groups where you don't have adequate information or knowledge about what to expect under the control. And in that case, I would argue that you shouldn't be doing a randomized, double-blind, very large phase 3 type clinical trial. You would probably want to do some kind of a pilot study to get a good estimate of what happens in your groups in order to adequately power a larger study. In addition to understanding what could happen under the control condition, you need to also specify what you want to see in the experimental condition. That's the difference that you wish to detect. The way that you specify this is you have to ask yourself, either from the literature or from your experience or from what the standards are in your field, what difference is clinically meaningful. You may find in studies that are either overpowered or underpowered that statistical significance is not always linked to clinically meaningful differences, meaning you may generate a p-value that's small and then that actual difference is still too small to be clinically interesting. That's what's called being overpowered. Here, we're specifying beforehand what difference we want to see. We're tying it into the statistical significance through the power calculation. So if we get done with our study, we have an adequate amount of data. If that clinically meaningful difference is there, we will hopefully be able to detect it because we have an adequately powered study. Here, we want to be able to determine if the treatment halves the mortality relative to placebo. In other words, we want to be able to detect if the mortality rate drops down to 5% or lower. So this is like an upper bound on the expected response rate, the expected mortality rate in our treatment group. In English, it's our goal to identify a treatment that decreases the one-year mortality of patients to no more than 5%, which is half of what we would expect in patients who are treated with a placebo. In English, we would also like to be pretty confident that we can detect this difference if it exists using the chi-square test that we have in our analysis plan. The 90%, for those of you who recall from last week, the 90% relates to the power of the test. So we can specify the power of 90%, and that would tell us how frequently, or what's the probability of missing this meaningful effect if it in fact exists. So we're controlling the type 2 error rate at 10%, no bigger than 10%. In order to power the test, we have to lay out the information that we have, our null and our alternative, which is our research question. Are the mortality rates, the one-year mortality rates, the same or are they different? This is a conservative two-sided test because I want to also be able to detect if this therapy hopefully doesn't, but it could potentially increase mortality. And if that happens, I want to be able to detect that difference as well. My type 1 error rate I want to control at 0.05. My type 2 error rate I want to control at 0.1, which means I'm basically setting my power at 90%. And that clinically meaningful difference needs to be 0.05 because I think under the placebo I should see a 10% mortality rate. I want to have that, which would be a difference or a change of 5%. You can power this test very easily using the power.chi-square.test function in R. I'm not going to go out into RStudio and do this, but I do have screen captures of this information. It's probably not that easy to see, actually. What you end up having to put in to R, if you can see here, are the null hypothesis proportions. Basically, what is the null hypothesis in terms of the proportion of the mortality rate in the placebo and in the control? Well, we think that for the placebo it's 10%, so no difference would result in having the same mortality rate in the treatment group. So that's 0.1 and 0.1. Just like we specified probabilities in the previous example for the chi-square, we're doing it in the same way. We're saying combine these two elements together and call them P0 to represent our hypothesized proportions. Then we have to also specify our alternative hypothesis, and this is that clinically meaningful difference that we want to see. We want 5% in the treatment group, 10% in the placebo group. We combine them together and give that to an object called P1, which represents, again, our specific alternative hypothesis, that minimally clinically meaningful difference. In order to feed the correct information into the chi-square test, we have to compute this effect size. Now, we don't have to do it by hand because, again, the benefit of R is that there are people all over the world who are contributing functions and packages to this in order for you to do analyses without having to hard code everything yourself. So someone else has a function that will compute Cohen's effect size for this kind of analysis. And I've given you here the formula for it, where we basically have the mortality rate under the null hypothesis, the mortality rate under the alternative, and it's done over both the treatment group and the placebo. And it's basically like a chi-square test where you're looking at the deviations between what's observed and what's expected. But the ES.W1 will compute that W for our two sets of probabilities, our alternative hypothesis probabilities and our null hypothesis probabilities. Again, I don't like the usual conventions of classifying effects as small, medium, or large. I think that a small effect in some contexts could be very meaningful, and in other contexts it could be not meaningful. So it's up to you to determine what the appropriate effect size is if you're working directly from these effect size metrics rather than actually specifying what P1 and P2 should be. Using R, the way that we compute it is we simply call on the power.chi-square test. We give it our effect size that was calculated from our proportions. We tell it what our significance level is, and we tell it what our power is. And then the results output gives you the power and the estimated sample size. So for the effect size, the 5% reduction in mortality at a 5% level of significance with 90% power would require 421 subjects for this study. That's the total number of observations, put half in placebo, half in treatment. So if I were the statistician on this project, I would have to justify my sample size calculation, my estimate, after I've specified my analysis plan. So the overall sample size of 420, and technically it should be 421, you should round up, would provide us with 90% power to detect a 5% reduction in one-year mortality using the chi-square test, assuming I'm equally randomizing subjects to groups. In other words, I'm going to have equal sample sizes, a 5% level of significance, and a 10% mortality rate, expected mortality rate in placebo. Notice that there are a lot of assumptions here. Assuming we randomize equally, assuming a 5% level of significance, and also assuming that this is what we end up actually observing in placebo. If we don't observe approximately a 10% mortality rate in placebo, then my sample size calculation may be off. I may actually be overpowered or underpowered. That's why it's important to have some degree of flexibility in your design where you may have to reassess your sample size calculation at some point, but you would pre-plan for that. There was one other thing I was going to say. I don't remember what it is now, but that's how you would power a simple chi-square test. Any questions about this information? Let's get into survival analysis. So survival analysis, I'm sure most of you are familiar with this at some level. It's simply the way that we treat questions where we're interested not only in whether or not an event is occurring, but what the timing of the occurrence actually is. This is a unique kind of data because it combines both a categorical piece of information, so the yes, no, the event occurred or did it not, with a continuous outcome, in particular a time of the occurrence. The event, even though we call it survival analysis, the event could actually be the development of a disease. It could be time to a particular type of response to treatment, whether or not they responded or ended up having a relapse It could be time to death, it could be time to rehospitalization, it could be any event of interest where you have a uniquely defined beginning, origin, time origin, and a uniquely defined endpoint of that time interval. Survival time, we often see it represented using what are called Kaplan-Meier curves, but by definition it's again just the time from some well-defined point in time to the occurrence of the event. When we get data that's survival data, we have more than just whether or not the event occurred, which is the event status, but also a time of occurrence and then any other relevant subject characteristics. If we wish to adjust for these other relevant subject characteristics, we could do stratification, and where you would plot Kaplan-Meier curves by subgroups, or you could do actual regression methods using Cox regression. Survival data is a unique kind of data because we may end up having what are called censored observations. Censored observations occur when, if you're in a clinical study situation, very often we have a fixed study period. So we get funding from the NIH to do an R01, and we've determined that we really only have, let's say, 4 years for the study period. So I have to get all my patients enrolled, I have to treat them, and I have to follow them for their response. I may have a predefined 1-year term of follow-up. So patients are going to they're going to come in at different times, and I'm going to follow them for a specific length of time in most clinical trial scenarios. What may end up happening, though, in these longitudinal studies is that you may have patients who are lost to follow-up. They may just quit coming for follow-up visits. They may die from other causes. They may withdraw consent. There's lots of reasons why you wouldn't get complete follow-up on a patient whose survival time you're interested in. So these are what are called censored observations, and what we end up having to record is information about what period of time we knew they were actually surviving. So they came into the study at the beginning, and we were able to follow them out for 9 months, but at 9 months they quit coming. We lost contact. We have no idea what their status is after 9 months. So in the data set, we would still have a time. It would not relate, though, to the time of the event occurrence. It would actually relate to the last time we had contact with them, and that would be the time at which we would censor them, which would basically say they survived for 9 months, but we have no idea what happened for the remaining 3 months of the study. Another way that we would censor observations would be if we had patients who did not experience the event by the end of the study period, by the end of the follow-up period. So if we have patients who are still alive, if death is our event of interest, patients who are still alive at the end of the study, at the end of 1 year of follow-up, then we would record that time. We would record 12 months. But then we would censor them because they didn't have the event. If we have no censored survival times, which means that every patient or every subject in our study had the event within the study window, then we have complete data. And that's, at least in my experience, not something that I'm usually working with. Most, if not all, survival analyses that I've had to perform have had some kind of censoring associated with them. So when I say censoring, what is censoring? Censoring is just a unique form of missing data. So we'd have some level of information, but not complete information on each subject. So here for subject A, we were able to follow them over the entire study period, but we actually are not allowed to know or to track them after the end of the study period. They may have had the event 2 months later, but it will not be included as information in our analysis. So they would be censored at the end of the study. The time would be recorded, and then we would record that they did not have the event. This person, subject B, we followed them, and they ended up having the event prior to the end of the study. So here, we would be able to record not only the timing of the event, but yes, the event occurred. Patient C, we lost them to follow-up. At this point, they quit coming for follow-up visits. That was our date of last contact. So unfortunately, we could say we know that they survived to this point, but beyond that, for the remaining part of the study period, we don't know what happened to them. They could have had the event here or not. So we have to actually record this time so they can contribute information to the analysis up until this point, and then they can no longer contribute. And they're censored here, so we also don't allow them to contribute to the count of events because we don't know that they had it. And then subject D, of course, they go on off the page without having the event. So they would actually, their data would look identical to the data for patient A, for subject A, because what we would see during the follow-up window is no event. They would both be censored at the end of the study, even though subject A had the event shortly after, and subject D did not. And this is what the data set would look like for each of the subjects, their time, and then whether or not they were censored. There are some different functions of survival time that are interesting to us. I already mentioned the Kaplan-Meier curve, which is an estimate of the survivor function or the survival function. The survival function conveys to us the chances or the probability that an individual will survive longer than some time, t. T is the x-axis. That probability is on the y-axis. Here's an example of a Kaplan-Meier curve, which is an estimate of the survival function. And again, the vertical height of this function represents the probability that a subject in this group will survive to the time that corresponds to the location on the x-axis. So if I have time since diagnosis in months on the x-axis, then I can look at this treatment group represented by the straight line. I can determine what the median survival time is by finding the vertical distance of about 0.5. This is the point at which 50% of patients or subjects are still surviving, and find where that curve crosses that point and go down, and that gives me an estimate of the median survival time for this group, almost 30 months. I can compare that with the other group, which actually has a lower median survival time, somewhere between 18, probably about 20 months. That's one of the ways that we would be able to visually assess differences in groups. So of course, when your benefit is in terms of extending survival or increasing the chances of surviving to a given time point, what you hope to see are curves that are closer to the upper right-hand quadrant of this plot. The closer it is to the plot, the better performing treatment the treatment actually is in terms of extending, pushing out survival, delaying events, and also keeping the probability, the survival probability high over time. So very quickly we can see that this curve, this group represented by the straight line, actually has improved survival relative to this curve with the dotted line. Here I've given you a very common statistical method for comparing survival functions between groups. That's called the log rank test, and this P of 0.01 tells me that the survival functions are different over the entire study period. Another useful tool from survival functions, from survival analyses are the hazards. Hazards are a little bit more difficult to understand, but if you understand something like an odds ratio, you can understand a hazard ratio. All a hazard does is describe the instantaneous event rate. So if I'm looking at the survival function is describing the probability of surviving up to time point t. The hazard function narrows it down to a specific small unit of time and says, what's the probability of having the event in this small unit of time given I've survived up until that event? So if we just take a look graphically at some different ways events could be occurring, if I have my study period defined by the x-axis, so the beginning of the study period all the way out to the end, this origin could be the day they were diagnosed with the disease or the day they started treatment. And then the hazard, again, we're describing if it's higher, then the risk of dying at a particular time point is high. If it's lower, then your risk of dying is lower. I can see how the risk of death or the risk of the event changes over time. For this green line, subjects are more likely to die sooner. As we move out in time, the risk of death is decreasing. The reverse is true in the situation described by the red line, where the risk of death is very low early in the study period. In other words, I shouldn't be seeing a lot of events. My survival function was probably flat or not decreasing very quickly. But as I move through the study period, I'm seeing events occurring at a greater rate. So the risk of death is increasing as I move across the study period. And then we can see what are called bathtub-shaped hazards, where you have a high risk of death early, that goes away, maybe treatment starts to work, but it only works for a period of time to keep that risk down, and then at some point treatment stops working and the disease progresses and risk of death goes back to what it looked like at baseline. Hazards are very useful in describing what the risk is of having an event. They're also very useful for comparing groups, and I'll talk in a moment about what a hazard ratio is actually representing. In survival data, the easiest way to think of the hazard function is when you have no censored observations. In other words, you are able to observe the event occurring in all subjects in your study. In that case, the hazard function is estimating the proportion of patients dying in a specific period of time, whether it be within a week, within a month, within a year, given that they have survived to the beginning of the interval. So think about when you report a hazard for a clinical trial. If your period of time of interest is 1 year, so you're interested in 1 year survival, if you report a hazard for that 1 year, then you're saying once treatment starts, the hazard represents the proportion of patients dying within that 1 year, given that they were alive at the end of treatment or the beginning of treatment, whatever I ended up saying. And that's what a hazard is doing. So when we compare hazard ratios, we're basically comparing proportions, mortality, if you will, mortality rates between groups over a particular period of time, whether it be 1 year of follow-up, 5 years of follow-up, 10 years of follow-up. The problem with reporting a hazard or reporting a hazard ratio for these long periods of time is that we're making the assumption that the chances of dying in a year are constant over the entire year, and that's not the case. So if you're familiar with Cox regression models, one of the part of the name of the Cox regression model is what's called the proportional hazards model, and that's an assumption of the model. The proportional hazards model could give you a hazard ratio comparing groups, but it's making the assumption of there basically being a constant treatment effect over time, meaning if you're comparing treatment A and treatment B, treatment A is better over the entire study period, and it's better over the entire study period in the same degree, for instance, over the whole year. And that's not always the case. Very often, what we'll end up seeing with Kaplan-Meier curves are different treatment effects. Proportional, this is what Cox proportional hazards regression is assuming. And this is also what you're assuming when you report a hazard ratio comparing two groups over the entire study period. I'm assuming that the treatment effect, which is represented basically by the distance between these two lines, is approximately the same over the entire study period. If it is, then a hazard ratio will do a very good job of telling you something about the benefit of treatment over the entire study period. However, if you have Kaplan-Meier curves that converge, which basically means I see a difference between them early, but by some point late, they actually end up having the same exact survival estimates. If that's the case, then providing a hazard ratio that tries to summarize the overall effect of treatment will basically average benefit with no benefit, and it'll give you a little bit of a biased look at the comparison, unless you're trying to look at the overall benefit over the entire year. You can also, if you're interested in describing a treatment effect using a hazard ratio, you may end up having a diverging set of Kaplan-Meier curves, which basically, if the curves are very close, then there's no difference in the survival or the event rates up until here about 20 months. But at 20 months, we see that this group defined by the black line continues the trajectory it was on. But the one that has, as defined by gray, the event rate actually flattens out. So your hazard here, your risk of death is changing. Once it gets to about 20 months, your risk actually increases because the events aren't occurring with as much frequency as they were before. And again, if I tried to provide a hazard ratio, the hazard ratio would average no effect with some effect. So you might actually end up with, you would end up with a single number that could describe an overall average treatment effect, but you may miss out on these meaningful differences that occur later, which is why sometimes it's important to say, what's the hazard ratio at 40 months? What's the hazard ratio at 60 months? What's the hazard ratio at 80 months? What's the hazard ratio at 20 months? So you get an idea of, it's almost like having an interaction between treatment and time. That's what's called a time-varying effect, which means your treatment, the effect of treatment is not constant over time. The hazard, I keep saying hazard, it's basically just another measure of risk of an event, but it's also a very interpretable metric. Not the hazard ratio, by the way, just the hazard, which describes the risk of the event occurring at a particular time t in a single group. So for instance, if I compute the hazard for a population in terms of the timing and occurrence of influenza, and I see that the hazard is 0.015. So a patient's hazard for contracting the flu is 0.015. And I'm actually, the time measurement, the unit of measurement of time is in months, not in days or years, but in months. Then I can convert this by multiplying, for instance, by 12 to get a hazard for a year, or I can multiply that by 10 to get what would look like a hazard for a decade. And it's a little bit easier to see in terms of decades because the hazard is so small. But the interpretation of this would be that the patient could expect to contract the flu twice over the course of 10 years, assuming the risk of the flu is constant, or the hazard is constant. And that's the interpretation. So it's not only sort of a probability of it occurring, but what is the probability of occurring over a particular unit of time? Log rank tests are the way that we compare survival between groups. Log rank tests are really good when you have a constant treatment effect. In other words, your treatment effect is not changing over time, where you don't have diverging curves or converging curves or curves that cross, which can often happen as well. If that's the case, the log rank test will be underpowered to find those differences. If you think you have, for instance, short-term differences in survival, like this converging, so you see benefit early on that goes away later, or diverging, which is a long-term benefit that doesn't really exist early on, you may want to choose a different type of test prior to seeing your data, by the way. You wouldn't want to choose the data or choose the analysis method based on what you see in the Kaplan-Meier curves. You should probably anticipate some difference first select the test first, then do the experiment or collect the data, and then perform the analysis. But there are options here which basically provide weights, higher weights, to events that occur either earlier in the study period or later. The Wilcoxon test tends to be better or more powerful detecting short-term differences. The Prentice gives higher weights to earlier events, so short-term benefit. The Fleming-Harrington actually allows you to specify your weights. So if you think that the benefit's in the middle, towards the end, or the beginning, it allows you to specify those weights based on what you are interested in detecting. Here's an example looking at two different types of therapy, radiation therapy, for patients with carcinoma of the head and neck. Researchers are interested in exploring differences in survival between patients that were treated with accelerated versus standard fractional radiation therapy. The problem with this study, though, is that it's based on medical records, patient charts. So there was some degree of clinical decision-making that went into assigning treatment to patient that we can't necessarily account for in an analysis. The one thing that we can do, though, is look to see how the two groups, the two treatment groups, look in terms of other potentially prognostic factors for response. So we can look at the distribution of gender. It looks very similar, except for the fact that the standard therapy is all male as opposed to having one female in the accelerated group. We can look at their ages because theoretically age should have an impact on their response, and they're about the same, 61 and 65, 30 to 71, 43 to 78. We do have a few younger patients, or at least one patient who's a little bit younger than the average in the accelerated group. We can look at the site of disease to see if there's any difference. We can also look at the stage of the disease and the tumor staging criteria. One of the things that pops out right away to me that could potentially cause differences in outcomes is the fact that we have a preponderance of stage 4 disease in the accelerated treatment group, whereas it's pretty much a 50-50 split in the standard treatment group. We also see increasing tumor stage, or a higher tumor stage in the accelerated group, which tells me that clinicians that are deciding whether or not to give these patients accelerated or standard treatment may be taking into account the severity of their disease when they assign the treatment. They may be putting people who are either younger and could withstand the accelerated, more intense therapy onto the accelerated group. Maybe they're putting people with later stage disease or more severe disease on this as well. So we have to be careful with our results whenever we talk about what differences that we see. One way to do that could be to stratify or to use a regression model to try to adjust out those confounding variables. Your hypotheses when you're looking at time to event data revolve around the survival functions. So you're interested in whether or not the two survival functions are the same over the entire period of time versus whether or not they're different at least one period of time. So this is what your hypotheses look like. Here's the Kaplan-Meier survival estimates for the accelerated group in blue and the standard group in red. What you see with the little dots, those are places where we have censored data. So for instance, there was someone who received the standard treatment that we had follow-up data on from some time point, some predefined time origin, which may have been the start of treatment, up until 6 months later. But at that point, we have no more information on their response. We don't know whether they died or not after this time point, so we censor them. Notice when we censor them, they don't contribute to any drop in the line. They just quit contributing to the analyses. They contribute here basically to the proportion of patients surviving, and after that, they don't contribute at all. And so anywhere you see a dot would be a censored observation. If we did an analysis, we could do the log rank test. I'm not going to do this in RStudio because I don't want to get into the complexities of survival data and all of the different issues with censoring because it would take up too much time today, and I'd like to get to regression methods as well. But this is very easily done using R. You can provide survival data for two groups and ask for the log rank test, and it will give you a p-value. So the interpretation here, and even visually, you can see that there's really not a difference in the overall survival between the two types of therapies. We have a log rank test p-value that reflects that. The 0.5 tells us that there's not really a difference. And in fact, the median survival time, which again is the x coordinate for where the survival function crosses that 50% threshold. It's 18.38 months in the accelerated group, but only there's only a benefit of about 5 months relative to the standard. So not a huge benefit in survival. And again, maybe now we should take a look at the impact that staging of disease has on survival. Well, the way we can do that is we can stratify our treatment groups by this confounding factor, stage. So now rather than having 2 survival curves, I have 4. My accelerated stage 3 is represented by the red. The accelerated stage 4 is green. So you can see that there's a huge separation in those 2 lines. Just within the same treatment, it appears that the accelerated stage 3 has overall survival that's much better than the accelerated stage 4. Again, curves that are closest to this upper right-hand quadrant demonstrate better survival. And you can see that there's not a lot of events occurring in that group. Again, we're also dealing with relatively small sample sizes here because we only had about 16 in each group. If we look at the standard therapy, when we stratify by stage, we don't see quite the separation between the blue and the teal, or the light blue and the dark blue. We do see that there is some separation once you get out to about 12 months, in that the stage 3 disease subjects their survival is greater in terms of both the rate of events is smaller and the duration of survival is longer. So yes, stage, when we compare the stages between groups or within a group, we do see that there is some impact on survival due to the stage. We can also then compare treatment groups within a stage. So if I wanted to compare stage 3 disease for accelerated versus standard, I would compare the red and the blue, and I do see that there is quite a bit of separation here. In fact, these 3 lines, the blue, the light blue, and the green, all kind of follow the same trajectory, with that light blue being the worst survival of all 4 of the groups. And that, of course, is the stage 4 standard therapy. In addition to visualizing the survival using Kaplan-Meier estimates, we can get a p-value for the comparison. The p-value here is 0.0792, which is statistically significant, not at the 5% level, but at the 1% level, and at least provides us with a hint of evidence that there is probably a benefit for at least stage 3 disease in this accelerated therapy. And we can describe the median survival time. So 50% of patients are surviving out to almost 80 months if they're stage 3 disease and they get the accelerated therapy, versus only 8 months if they are stage 4 and get the standard therapy. So again, it gives you an idea of the benefit for each of these treatments for different disease types or disease subgroups. So how do we interpret the hazard ratio? Is everyone familiar with the odds ratio? I'll actually cover that in a moment, but I think we talk about odds ratios as well. Odds ratios are generated from the same kind of data, where you have yes, an event occurred, or no, it didn't, but it doesn't have any information about the timing of the event. So it's basically just looking at the risk of the event occurring in one group relative to it occurring in the other. And that risk is measured by the odds. So of an odds ratio, which is comparing the odds of, for instance, death in the treatment compared to the death in control, if I get an odds ratio of 2, the interpretation is that death is 2 times more probable in the experimental group compared to the control. If I get the same value for a hazard ratio, remember hazard ratios come from data that not only tells you about whether or not the event occurred, but the timing of the occurrence. So if we have a time period of a year, and I compute a hazard ratio over that entire year comparing a treatment group to a control group, and I get a value of 2, then that hazard ratio interpretation would be that death occurs on average twice as often during that 1 year in the experimental group compared to the control. And again, that's a function of time. So I could compute the hazard ratio for a different period of time. I could do it for a month. I could do it for a week. I could do it for 10 years. And it would be telling me about how frequently it occurs during the time period. This is why it's so important to think about the interpretation, linking it back to the actual pattern that you see in the Kaplan-Meier curve. If you see curves that are crossing, then a hazard ratio might not be an accurate representation of the overall effect of treatment. You might need to narrow it down to smaller windows if you're trying to describe. Now, if your purpose is to say what is the benefit in the 1 year window, then the hazard ratio will give you an average benefit. But when you average out, you might be missing if you're interested in identifying early or late benefit, you would need to narrow your window down to earlier periods and later periods, and you could potentially compute hazard ratios for those time periods and get a more meaningful interpretation of any treatment effect that you have.
Censoring the data affect hazard ratio compared to odds ratio? Not censoring?
Yes, it will. Yeah, censoring affects the hazard ratio. Yeah.
Not the odds ratio.
Well, the odds ratio, censoring in that case would be just missing data, which is so it would affect the odds ratio as well. Yeah, it would just affect it in a different way, and it depends on how you handle the missing data. If you had complete data and they both came from the same period of time, they would be the same thing, if that makes sense. Their interpretation would be a little bit different, but they would be the same thing. If you had censored data, then you could have very different results. Any other questions about survival analysis? I'll talk a little bit more about it when we get to Cox regression. If not, let's continue on into regression methods. Up to this point, we've really done very simple analyses where we just look at a single group or multiple groups and we compare some outcome between them, either their means or their proportions or even the time to the survival. What if we wanted to adjust these comparisons for other potential variables that we believe are related to the outcome, other than the actual treatment of interest? So even though we use randomization in clinical trials, there may still be factors we want to adjust for. Maybe we want to adjust for gender or age or some other what we call prognostic factor or risk factor or confounding factor. Regression methods will allow us to incorporate these factors into the test of a treatment effect. The most common approaches to adjusting are if we have a categorical outcome, like yes, response occurred or no, it didn't. Yes, death occurred or no, it didn't. Logistic regression would allow us to compare groups or even look at how that outcome, that categorical outcome, differs for different levels of a continuous outcome. Logistic regression can be implemented in R using a GLM. I'm only going to cover an LM, a linear regression example today, but in RStudio anyway. But logistic regression can be done in the exact same way using what's called GLM, the GLM function. The regression model that you're probably most familiar with if you took an undergraduate or graduate statistics course is what's called linear regression. The assumption around linear regression is that instead of having that binary yes-no response, your response is continuous. In fact, it's normally distributed. Then you can look at how that response is changing as a function of any kind of combination of categorical and continuous independent variables, your x's. The way that we implement that is through the LM, or linear model function in R. And you just specify your model and it will give you your model results. You can also do this in the context of ANOVA. And this is a specific type of linear regression where the only types of predictors you have are categorical. Linear regression, you can have continuous, categorical, or a mixture of them. In ANOVA, generally we only have categorical factors. And then, of course, Cox regression is the regression model that you can use to adjust for other variables when your outcome is that time to event outcome. Some important features or important points about linear regression. The relationship between two continuous variables in the simplest case may be one of a functional dependence. That is, if you're interested in how your outcome is changing for certain types of changes in your predictor, you're interested in estimating a linear regression model. You want to actually get out estimates that will describe how one changes as a function of the other. For instance, supplement dose and birth weight. Notice that dependent, meaning you think that your outcome is dependent on the value of the predictor, it doesn't necessarily mean caused by. We can't talk about cause and effect unless we have a study that's designed to detect causation. In its most basic form, with linear regression, we're basically estimating the equation of a line. So we have an intercept. I'm using the algebraic notation for a line, the mx plus b. The intercept and the slope, which represents the change in y for every unit change in x. We usually represent those by betas. Beta 0 is the intercept, beta 1 is the slope that describes the relationship between x and y. And then we have this random component. So rather than just this deterministic relationship like we saw in algebra or physics or whatever, we also have noise associated with our data, which is why very often when we plot x and y in a scatter plot, you see a cloud or an elliptical pattern rather than a straight line of points. And this is the simple linear regression model. If we had a deterministic relationship, our data would follow a straight line. The slope represents for every unit change in x, what is the unit change in y. And then the beta 0 component represents where the line would cross the y-axis. Here again, y is the response. X is the independent or explanatory variable. Beta 0 and beta 1 are those parameters that we're going to estimate. And epsilon is the noise in the data, the error. This is what data that we get usually looks like. It doesn't follow a straight line, but we fit a straight line to it. We try to estimate that functional dependence between x and y, getting what's called a line of best fit, and our data fall around it. So these epsilons describe the vertical distances between our data points and that line of best fit. So if these things are really big, then we have a lot of noise in our data. Our line isn't following or isn't doing a really great job of describing the relationship simply because maybe we have just too much noise in the data, or maybe we don't have our model specified correctly. But the 0.78, the beta 0 estimate, tells me that when x is equal to 0, y is equal to 0.78. And the 0.89 tells me that for every unit change in x, I can expect a 0.89 change in y. Here's a simple example on anthropomorphic measures from a random sample of children, 150 children, up to 12 months old. And we want to know what's the relationship between the average arm circumference and height in these children. The way that this would be implemented in R is using, again, that LM. I'm going to generate some fake data for this example, and then I'll show you in some graphs some of the ways that we can describe relationships. A potential option for looking at this, of course, is linear regression. There are actually other ways that you could get at this question. You could categorize things and do ANOVA, but linear regression allows us to describe the functional relationship. It also allows us to do prediction using that linear regression line. The line that we're going to get out, what it's representing is the mean value of the outcome for each value of x in the sample. And this will make a lot of sense, but only if we are reasonably assured that a line can describe the relationship. If you see something besides a line, you probably shouldn't be using a line to describe the functional relationship. So let me go into RStudio. I've got some fake data here. I've got my x, which will represent our predictor, and y represent arm circumference. This would come in the form of a data set, and you could call the variables something besides x and y, but I like x and y because it reminds me of which is my independent and which is my dependent variable for this case. If I wanted to look at a scatter plot of these two, a simple plot statement will work. I can do plot x, comma, y. X specifies what variables on the x-axis, y specifies what's on the y-axis, and that will create a scatter plot of the data. And I can see that a line probably would do a good job of at least describing the functional relationship between these 2 points. So I'm going to plot a line over this. The way that I do that is I use that LM function to fit a linear model. And then I give it to this other command called AB line. AB line just draws a line between 2 points. So I can give it the 2 points on my graph. I can say draw it between this point and this point. Or I can give it a slope and an intercept, and it will draw a line that's defined by that slope and intercept. So one of the outputs of this LM is a slope estimate and an intercept estimate. So by putting that inside the AB line function, I'm able to actually draw over my data that linear regression line, that least squares regression line, estimated from the data. So what is that actual estimate? This y tilde x is the functional notation in R, so if I had other x's, I could do x2 plus x3 plus x4, and that would be a multiple regression model. But I only have a single x in this case. And I'm going to fit that model, y is equal to beta 0 plus beta 1x, and I'm going to assign it to this object called fit so I can work with it a little bit more. If I type the word fit, it will display the intercept estimate. This is the estimate of beta 0 and the estimate of beta 1. Or I can use the summary function on that fit to get even more information, and that's generally what we want to work with. So in this case, the R output will give me a 5-number summary on my residuals. It will give me estimates of beta 0, the 2.7397, and an estimate of beta 1, along with their standard errors that describe, again, the sampling variability in this estimate. These are the things from which the t-test statistic is pulled and the p-values. I'll talk a little bit about the p-values in a moment when we get into the hypothesis testing, but they're basically saying, are these terms important to describing the variation in our outcome? And they both are, because our p-values are small, and this is scientific notation, by the way. We also get some other information like degrees of freedom. This is our MSE. For those of you who know, I'm not going to go into what MSE is, but you can take a look. The R squared. The R squared is a metric that's very, very useful in interpreting the quality of your regression model. This tells us that our model is describing 47.7% of the variation in the outcome. So the more variation we're able to describe, the better quality this regression line actually is. If this were very small, I would be concerned that it's really not a worthwhile model, because I'm not doing a good job of adequately either predicting or describing how y changes as x changes. And then my F statistic here is basically telling me, in this case, that I need this model. This model is better than no model at all at talking about arm circumference. Now, some of the assumptions, though, of linear regression revolve around assumptions that we've checked in the past. For instance, normality. We know that normality can be checked using a QQ plot. We can check normality using other visual descriptions. We can actually do other tests, statistical tests, to check for normality. We also have to have equal variance. Equal variance in this case is called homoscedasticity, and it's called that because what we basically want to see is the variation of points around this line be about the same. You don't want to see what's called a funnel, where your variation in y, your vertical distances between points are very small here, and then they grow as x grows. That would be problematic, because then it would not allow you to make really good inferences using the data. And the way that you could check either of these would be the same ways that we check them with the t-test. You can do a QQ plot on the residuals. Notice in R, even though it doesn't display everything, there are some things kind of hiding under the scenes. I can get out of summary. I can get the residuals out by calling on them. The way that you call on these things, there's some specific language that you would have to learn, but it's actually pretty easy. I could call for a QQ plot, just like we used with the t-test and the ANOVA example, on the residuals. Summary, fit, residuals. So what I'm asking for here is for this fit object, within its summary, the $ tells R the name of the object I want to plot, the residuals. And I want to do it with a QQ plot. And I also like to overlay the line that this data should be following using the QQ line function. So I see here for this data, even though there are some problems out here in the tails, maybe we have a little bit fatter or thinner tails, it seems to follow the line pretty well. So I think that I have not violated the assumption of normality. I can also take a look at my previous plot, and I don't see anything here that tells me that the variation in y, the vertical distances between y values at a given value of x, is changing. If you see a nice ellipse, then you know that you've probably met that equal variance assumption, or you could go about the analysis in the way that we did for some of the examples last time. So in addition to just getting a beta 0 and a beta 1 out, I'm not going to go into the data. I've actually got the real data, produced some of the information that's in this PowerPoint. We can look at the individual estimates of beta 0 and beta 1 and figure out what information we can glean from this analysis. So, for instance, the 2.7 is the estimate of the value of y, arm circumference, for children who are 0 centimeters tall. So it doesn't really have any meaning in this case. It only allows us to fully specify the location of this line. We can also get estimates of arm circumference for specific values of height. So if we're interested in what the average arm circumference is for children who are 60 centimeters tall, then we just look at the value of that line at 60 centimeters, and that gives us the estimate. If we plugged it into the equation, which we could do in R, doing some simple calculation, we would get an estimate of 12.3 centimeters for children who are 60 centimeters tall. The parameter that's usually the most interesting to us is that slope parameter. The interpretation of that really represents how the outcome or the response is expected to change for given changes in the predictor. So in this case, the average change in arm circumference for a 1 unit increase, in this case a centimeter increase in height, is equivalent to the 0.16. So it's a 0.16 increase in 0.16 centimeters increase for every 1 centimeter increase in height. That's the impact on arm circumference, which is what I have listed here. So taller children have greater average arm circumference. And for 2 children who are 10 centimeters different in height, for instance, children who are 60 centimeters tall versus those that are 50 centimeters tall, we can also estimate the average difference in their arm circumference by plugging in values to this regression equation, which would correspond to x locations of 50 and 60, and it would give us back out this distance on the y-axis. In that case, it would be a 1.6 centimeter difference in arm circumference for children who are 10 centimeters different in terms of their height. One of the problems with regression is trying to extrapolate. So if I was going to try to make predictions or estimations using this line, I have to limit those predictions and estimations to where I actually observed data. For instance, the minimum value of x is close to 40, the maximum value of x is close to 75. I should not try to predict the outcome of arm circumference for children who are taller than about 75 centimeters or who are smaller than about 40 centimeters, because what we may end up seeing is this linear relationship may no longer translate to those ranges. And we would be doing what's called extrapolation, which is not really a valid way to use linear regression. I've already talked about the intercept, that in many circumstances it's meaningless. It's just necessary for fully specifying the equation of the line. Sometimes, though, it is important to know what the expected outcome is when x is equal to 0. For instance, if you have if x represents the dose of a medicine, x equals 0 would be like a placebo. When we're making inferences using linear regression, the hypotheses are usually, if we're looking at, is there a relationship between x and y versus is there not, the hypotheses are around that slope parameter. Our null, which is a statement that no relationship, no significant linear relationship exists, is a statement that that slope parameter is equal to 0. And our alternative is either one-sided or two-sided. If it's two-sided, we're saying that there's a strong linear relationship. It's either a negative or a positive. In other words, our slope is not 0. If we think it's a positive relationship, then we think our slope is greater than 0. If we think it's negative, we think it's less than 0. And this comes to us in the form of a test statistic that has a t-distribution. The formula is very different from the t that we saw last week, but it still behaves like a t. So we know that we can use and interpret it in the same way. The t-test statistic for testing whether or not there's a significant linear relationship comes in this coefficients table. So x is our predictor. The slope estimate is 0.99. So what we're estimating, at least from this data that I have in R, is that for every 1 unit change in x, we can expect about a 1 unit change in y. Here's the t-test statistic, which tells us what's the difference between what we observed and what we expected under the null hypothesis, which would have been an estimate of 0. And that p-value is very, very small. So we can conclude that there's a very strong linear relationship here that the relationship is a positive one. In other words, for increases in X, we see associated increases in Y because the estimate is positive. If we took this and extended it out to the situation where we have more than one predictor, that's called multiple linear regression. So right now, the data that we have is simple linear regression. If we had more than one predictor, more than one X, we would have multiple linear regression. These betas still represent essentially the slope or the functional relationship between their individual X and the outcome Y, but there's a little bit different interpretation that needs to be made, because not only are you accounting for how X1 affects Y, but you're also simultaneously accounting for how these other predictors account for variation in Y. So you have to take into account the other predictors when you're interpreting the effects of a single predictor. Here's a quick example to facilitate discussion about interpretation of these. Suppose we have a linear regression model where Y is the birth weight of a baby, X1 is the dose of a particular type of drug or supplement, X2 is gestational age, because we know that gestational age has an impact on birth weight, and X3 is gender. It's a categorical covariate gender, because we also know that there tends to be differences in birth weights that can be a function of gender. What we're really interested in is X1. How is this dose affecting birth weight? But we need to control for the effects of gestational age, because they may differ in these babies, and gender, because we'll have both boy babies and girl babies that could be different just because their genders are different. If I get out an estimate of beta 1, let's say beta 1 is equal to 1. The interpretation of that estimate is that among babies who have the same gender and the same gestational age, for every 1 unit change in dose, you can expect birth weight to change by 1, whatever the unit is, gram, I don't know, pound, probably not pound, that's a lot. So the key here is that if we hold everything else constant, beta 1 describes how babies' birth weights differ if the babies are similar in all other respects except the dose of the drug. It is not the same interpretation that we had in the simple linear regression situation where we just only had one thing we were accounting for, and that described how Y changed for it. Are there any questions about interpretation in multiple linear regression? The way that I would fit a model that looks like this in RStudio would be the way that I had typed it in before. You would have Y tilde X1 plus X2 plus X3. The second kind of regression that's probably a little bit less well known, because I don't think it's taught in undergraduate statistics courses, is called logistic regression. The only way that this is different, if you remember the equation of a line, we still have that, but now rather than having just Y on the left, we have something called the log odds. The reason that we do this is because it's no longer appropriate to assume that there is a linear relationship between our dichotomous or binary outcome and some predictor X. If you plot binary data on the y-axis, it's either going to be 0 or it's going to be 1. But if we think the chances of the event occurring, which would be a y equal 1, are actually related in some way to some covariate like temperature, then you might actually see a separation in terms of the x-axis between non-events and events. And the nice way to link some covariate with this response, 0 and 1, is through the logistic function. And the logistic function requires us to have this logit function over on the left in order to give us a linear relationship between x and some function of the outcome. So here, if y is binary and x is some kind of predictor, what we're actually modeling in logistic regression is the risk or the probability of the event, specifically the odds or the log odds. The interpretation in this case, you can see because of the weird look of the regression equation, it's not quite as straightforward as it was in linear regression. For instance, if I left beta 1, that slope parameter, in its untransformed state, its raw interpretation would be what is the expected change in the log odds of the event for every 1 unit increase in x. And that's not really interpretable. So what we have to do is once we estimate beta 0 and beta 1, we actually do a transformation of those variables using a natural log in order to get out something called an odds ratio. And the odds ratio is very simple to get. You simply exponentiate your estimate for beta 1. And an odds ratio I'll get to in a moment in the interpretation. Let's look at an example here where we're looking at the odds of death. So the result of this will be getting estimates of beta 0 and beta 1 that describe how to relate some covariate x, in our case it's going to be treatment, either intervention or standard of care, to the log odds of death. Pi here we're representing as the probability of death, the probability that y is equal to 1, and x is equal to 1 if the subject received the intervention and equal to 2 if they received the standard of care. The way that you would fit this model in RStudio would be through a GLM, very similar to what we did for the LM, but you would have to tell it that you have binomial data, which means that you have your outcome is a yes or no outcome. So suppose we fit this data and we get out estimates of beta 0 and beta 1. We're describing the relationship between treatment and mortality. Suppose from that output beta 1 was estimated to be negative 0.69. We can't interpret that alone. What we have to do first is exponentiate it in order to get the odds ratio that relates treatment to the probability or risk of death. So if I exponentiate e to the negative 0.69, I end up with a value of 0.5. So this is the odds ratio that relates the probability of death, the risk of death, to treatment. Treatment is on the numerator, control is on the denominator. So if I get an odds ratio of less than 1, if the odds ratio is equal to 1, then the odds of death are the same. They're equivalent. If it's less than 1, that indicates some kind of reduction in the odds associated with treatment. If it's greater than 1, that indicates an increase in the odds with respect to when you get treatment relative to control. So here the interpretation would be that when treatment involves the intervention, the odds of dying decrease by 50% relative to the standard of care. We can also, once we get that estimate of beta 1 out, see very quickly whether we have a decreasing relationship or an increasing relationship by looking at the sign of the beta 1 estimate. Since this was negative, before we even exponentiate, we will know that we'll get an odds ratio less than 1. In other words, a decreasing risk of death associated with the treatment. But again, it's difficult to interpret without that transformation. If beta 1 was estimated to be 0.41, that's our beta 1 from our fit of the model. We exponentiate that. Notice the sign is positive, so now we know that there is an increasing risk or an increasing odds of death, because exponentiating that will result in a value of the odds ratio greater than 1. And the interpretation of this is that when treatment involves the intervention, the odds of dying increase by 50% relative to the standard of care. So for odds ratios, a value of 1 means they're equivalent. Some distance away from 1, either positive or negative, describes the percentage increase or decrease in the odds of the event. When x is continuous, we can still do the same thing. Suppose now that y is death, but x is age. If we exponentiate the beta 1, which describes how the log of the odds change for every 1 year increase in age, we can get out the odds ratio. So it looks like we have increasing odds for increasing age because we have a positive sign in front of our beta 1. And if we exponentiate it, we get a 1.1, which if we interpret this in the context of our continuous covariate, it means that for every 1 year increase, whatever the unit is for age, for every 1 year increase in age, the odds of dying increase by 10%. In the same way that linear regression can incorporate multiple covariates, logistic regression can as well. If we wanted to interpret the regression coefficients, we would have to say this is the impact on the odds if we hold all other covariates constant. And then for Cox regression, I'll call her in just a second.
Yeah, she's waiting.
Okay, thanks. For Cox regression and logistic regression, they're actually very similar. Both are trying to describe a yes-no outcome, but Cox regression is doing it with a timing component. So it's incorporating the timing of the outcome in the modeling of the data. What you end up getting out of Cox regression versus logistic regression, you get that hazard ratio rather than the odds ratio. So there's a little bit of a distinction that we need to make here between what's called a rate and a proportion. An incidence rate or a hazard rate describes the number of events per population at risk per some unit of time. So again, there's a timing component. It may be a month, it may be a day, it may be a year, it may be a decade. The cumulative incidence represents the proportion of events that occur in the given time period. So the hazard ratio is actually a ratio of those incidence rates, whereas the odds ratio is a ratio of proportions. And this kind of gets to your question about how missing data impacts them and how you could end up with different things. Logistic regression will estimate the odds ratio. Cox regression will estimate something very analogous, the hazard ratio. The only difference is that Cox regression is taking into account the timing in addition to whether or not the event occurred. And we already talked about some of the patterns that you can see here where treatment can interact with time, and that particularly occurs when you see converging functions, diverging functions, or even Kaplan-Meier curves that cross. So we have to be careful using Cox regression to make sure that we do in fact have a treatment effect that does not interact with time. Some of the ways that we can, I've already talked a little bit about Kaplan-Meier. Kaplan-Meier is a non-parametric method, so it doesn't have any assumptions. It makes no assumptions about the data. But Cox regression does make some assumptions. It's called semi-parametric in that we assume that we have that constant treatment effect over time, or proportional hazards. For example, we could have a violation of that proportional hazards assumption through something called a time-dependent treatment effect. Here we could be evaluating the effect of taking oral contraceptives on stress fracture risk in women athletes over a period of 2 years. The problem with this is that the treatment could be changing. We could be switching on or off oral contraceptives, so it'd be very difficult to get out using just Cox regression and assuming a proportional hazards model any effect of oral contraceptive use on risk of stress fracture. If you just examine risk by a woman's status at baseline, you may miss any meaningful effects. There are more sophisticated techniques, though, for incorporating starting and stopping times of oral contraceptive use in a Cox regression model. Unfortunately, that's really beyond the scope of what someone without some formal training in statistics could do on their own. So I would encourage you, for any survival analysis really, if you're interested in performing one, that if you're not well versed in the methods that you don't just run a Cox regression model without first consulting someone who has the ability to check whether or not you've met those assumptions. And we're actually at the end of time, which is good because I've got a little slide here on the course evaluation. I was going to have you access it via our website, but I think I'll just send out an email, and that way maybe you'll be more likely to take it. It will take you to a link in REDCap where you can fill out some information on basically the usefulness of the presentations, the content, the organization, the pace, the level of difficulty, that kind of thing, and give me some feedback on topics like what to keep, what to add, what to do more of, what to do less of for subsequent years based on what you saw this year. Are there any questions about the material before we go? Make sure that we don't have any here. No questions? Okay, this recording, along with all of the other recordings, will be posted on our department web page under Events and Lectures. I will also send out an email that when I include the evaluation form, it will include all of the presentation materials as well. I think that you've already received the first two, but I can just send all of them again together just in case you have deleted that email or you want them all in one place. All right, thank you all for attending.